Okay. Sound. We're going to cover sound separately. It gets its own little discussion here because there tends to be some problems. Problems come up with this, largely because sound and sound intensity levels will refer to logarithms for reasons I'll get to in just a moment. And if you haven't worked with logarithms in a while, if the mathematics is unfamiliar to you, that can be a problem. So this is here to try and address that. Now, I'm going to take a rough approximation and just say that I've got some wave releasing power, energy over time, and I'll have those connections to, you should look at D2L to find links to material from the first semester that you may practice with and that you may refamiliarize yourself with as we go. Now, let's see, I'm treating this as each sound source as simply a point radiating universally into space. Day-to-day life, you can cheat. You can try and avoid that. If you put your hands up like this to yell at somebody, what you're trying to do is you're trying to limit the range, the area over which that energy is spread out. Because if it moves out on this circular sphere, well then each one step down the line, you're going to have that energy more spread out, more distributed, and the power per surface area, which is going to turn out to be what's very important here, will become weaker. And the power per surface area is the intensity. And the intensity is given in watts per square meter. However, what we have here, if I were to double the intensity of a sound, it wouldn't sound twice as loud to us. Well, that's good. Consider if you're listening to, somebody whispering at the table next to you, so as not to interrupt, like, face-to-face class. If that's happening, then you can hear that person. But if you could hear that person and twice the intensity meant twice the loudness to you, then the next time you step into a rock concert, your head explodes, and not in a good way. As it turns out, the ear, the eye, we don't have our response scaled, linearly. It's scaled logarithmically, so that, if I have, let's see, let's take some level I naught, which is going to actually be quite small. 10 to the minus 12 watts per square meter. And that sounds, very tiny. It's less alarming when you stop and consider that, say, your eardrums are way, way smaller than 1 square meter. So the energy is the intensity, the power per square meter. The power over your eardrums would then be larger. But if you have, the power, it will look small. It still matches up well. As you'll see, sound doesn't itself carry a tremendous amount of power to you. That's good. You don't want to have it feel, you don't want to have an energy per square meter like somebody was digging a nail into you every time they're talking to you. It only feels like that sometimes depending on who you're talking to. Now, this to average humans counts as barely audible. A little bit better if the younger that you are, the fewer loud concerts or construction crews you've worked on. And if you wanted to have the threshold of pain is much larger, which would put it at, let me just find, sec. Okay. And let's see, if the threshold of pain is substantially higher, quick back to the envelope, I hope I don't have to go back and re-record this, puts it about 20 times that power. That's at the level of pain. But it's not evenly distributed. So what we're going to do is we're going to take this power, not directly connected to what we hear, the intensity, also not directly connected with what we hear, and the sound intensity level, and define the sound intensity level with beta now. The sound intensity level is typically measured in decibels, where a bell is 1 unit of sound intensity level. But if we use decibels, then we go from 0, barely audible, to 130 and above, and 130 decibels is about the level of pain. So spread it out over around a range of 100. That's a good working range for people to work with. People are typically comfortable working with 0 to 100. And so that is equal to 10 decibels times the log base 10 of the intensity of the sound that we're listening to divided by this base level. And that will give me the sound intensity level in decibels. So, if I had an intensity level of, say, 2.3 times 10 to the minus 11 watts per square meter, then I over I naught would be 2.3 times 10 to the minus 11 watts per square meter divided by 10 to the minus 12 watts per square meter, which would give me 23 watts per square meter will cancel out. 10 to the 11th divided by 10 to the negative 11th divided by 10 to the negative 12 is 10. So that would be 23. So the sound intensity level at that point would be 10 decibels times log base 10 of 23. Now, the way logs work is that if I have the log in base A, the log in base A of B is equal to C, then basically what I'm saying is that A to the C power will give me B. So the log base 10 of 23, well, 10 to the 0th power is 1. So the log base 10 of 1 is 0. The log base 10 of 10 would be 1, and the log base 10 of 100 would be 2, because 10 to the second power is 100. So the log base 10 of 100 is 2. So I've got a number between 10 and 100. So I would expect the log of 23 to be somewhere between 1 and 2. And hey, it turns out to be 1.36. So the sound intensity level is 13.6 decibels. In just a moment, the next thing that I will film and then post will be an example of working with decibels.